The eruption of Vesuvius on the 24th of August in 79 C, now believed by some scholars, based on archaeological and literary evidence, to have occurred in October of that year, began with a thunderous explosion that sent a column of volcanic material surging 18 to 33 kilometers into the atmosphere. Pliny the Younger, observing from Misenum across the Bay of Naples, described this column with the precision of a scientist and the wonder of a poet, comparing its shape to that of an umbrella pine tree, what volcanologists today call a Plinian eruption column in his honor. For hours, pumice and ash rained down upon Pompeii at rates sufficient to collapse roofs under their accumulating weight. Thousands who had not yet fled were buried, asphyxiated, or crushed. Then, in the hours of darkness, the eruption column began to collapse under its own colossal weight, generating pyroclastic density currents, superheated avalanches of gas and ash moving at hurricane velocities, that obliterated Herculaneum and eventually swept across Pompeii with thermal energy sufficient to kill instantaneously. What makes the story of Pompeii not merely tragic but scientifically and humanistically extraordinary is the quality of preservation that the volcanic deposits achieved. The fine-grained ash that settled over the city in the hours and days following the initial explosive phase gradually hardened around the organic materials it entombed: wooden furniture, garden plants, loaves of bread still resting in bakery ovens, and the bodies of those who perished. Over nearly 2 millennia, the organic matter decomposed within its rigid ash casing, leaving hollow cavities of perfect human and animal form. When archaeologist Giuseppe Fiorelli devised the technique of injecting liquid plaster into these voids in the 19th century, he recovered something almost supernatural: the frozen final postures of people in their last moments of life. A man shielding his face. A woman clutching a child. A dog twisted against its restraining chain. These figures transcend archaeology, becoming windows of shattering intimacy into a world that vanished in a single terrible day, preserved by the very violence that destroyed it, speaking across centuries with undimmed emotional force. In the shallow, sun-bright waters of the Sunda Strait between the Indonesian islands of Java and Sumatra, there lay throughout the 19th century a small volcanic island known as Krakatoa, anglicized in popular memory to Krakatoa, whose 3 coalesced volcanic peaks had not erupted in recorded memory with any great consequence. Sailors knew it as a navigational landmark. The Dutch colonial administration of the East Indies considered it unremarkable. Below this surface complacency, however, the geological machinery of one of the world's most volcanically active regions was preparing an event that would alter global climate, generate a tsunami of devastating reach, and produce a sound that remains, by scientific consensus, the loudest noise ever documented in recorded human history. The island sat directly above a subduction zone where the Indo-Australian plate descends beneath the Eurasian plate, a tectonic arrangement that has produced some of the most powerful volcanic and seismic events in Earth's modern history. In the months before August 1883, small eruptions and earthquakes had been noted with increasing frequency, but the scale of what was building beneath the island's calm exterior was entirely unimaginable. The final paroxysmal eruption of Krakatoa occurred on the morning of August 27, 1883, when a series of 4 titanic explosions tore the island apart over the course of a single day. The third and most powerful of these blasts, occurring at precisely 10:02 in the morning local time, was heard as far away as Rodriguez Island near Mauritius, nearly 5,000 kilometers distant, where the sound was recorded as that of distant cannon fire. Across Australia, across the Indian Ocean, across Southeast Asia, people reported mysterious booming sounds and felt concussive pressure waves. The eruption column reached an estimated height of 80 kilometers, injecting enormous quantities of sulfur dioxide and volcanic ash into the stratosphere. The resulting tsunami, triggered by the catastrophic caldera collapse that consumed most of the island, rose to a height of 30 meters and swept across the coastlines of Java and Sumatra, killing an estimated 36,000 people in minutes. The atmospheric pressure waves generated by the explosion circled the globe multiple times and were recorded on barographs around the world, providing the first global demonstration of Earth's atmospheric interconnectedness. The consequences of Krakatoa's 1883 eruption extended far beyond the immediate devastation of the Sunda Strait region, reaching into the skies above every nation on Earth and altering global weather patterns for years thereafter. The stratospheric aerosol veil created by the eruption, primarily composed of sulfuric acid droplets formed from the oxidation of sulfur dioxide gas, reflected and scattered incoming solar radiation on a scale sufficient to reduce average global temperatures by approximately 1 degree Celsius during the years 1883 and 1884. This seemingly modest figure conceals dramatic regional effects. Crop failures, unusual frosts, and disruptions to monsoon patterns were documented across multiple continents. Perhaps more visually arresting were the atmospheric optical phenomena. Sunsets and sunrises around the world blazed in extraordinary shades of crimson, purple, violet, and orange for months following the eruption. Artists of the period recorded these anomalous skies in paintings that atmospheric scientists have since used to reconstruct the volcanic aerosol loading of the stratosphere. The Norwegian artist Edvard Munch may have witnessed a Krakatoa-enhanced sky when he conceived the lurid, anxiety-saturated atmosphere that haunts his most famous painting. If Krakatoa claimed the spotlight of popular volcanic memory, its neighbor in infamy, Mount Tambora on the Indonesian island of Sumbawa, surpassed it in sheer geological violence by an order of magnitude that staggers the imagination. Before its catastrophic eruption in April 1815, Tambora rose to an estimated height of approximately 4,300 meters above sea level, making it one of the tallest peaks in the Indonesian archipelago. The Tamboran people who lived on its fertile slopes had maintained a distinct language, culture, and trading civilization entirely separate from surrounding Javanese and Malay cultures. The mountain had shown no significant eruptive activity in recorded memory, and its population, estimated at 10,000 living directly on the volcano, had no reason to suspect the geological catastrophe that was quietly accumulating pressure beneath their feet over years or decades of building magmatic intrusion into the upper crust. The first rumblings began in 1812, with small ash falls and audible explosions that were noted but not interpreted with appropriate alarm, a pattern of human underestimation that volcanic history repeats with painful regularity. The eruption of Mount Tambora between April 5th and 15th, 1815, represents the largest volcanic event in recorded human history, releasing an estimated energy equivalent to roughly 170,000 Hiroshima atomic bombs and ejecting approximately 160 cubic kilometers of magma and volcanic debris, a volume that dwarfs the outputs of both Krakatoa and Vesuvius combined. The eruption column on the evening of April 10th reached an estimated height of 43 kilometers, well into the stratosphere. Pyroclastic flows swept down all flanks of the collapsing mountain, incinerating everything in their path and reaching the coastline, where they generated local tsunamis. The entire summit of the mountain collapsed into a caldera 6 kilometers wide and 700 meters deep, erasing more than 1.5 kilometers of the mountain's original height in a matter of hours. The Tamboran language, with its speakers, ceased to exist that night. The death toll from the immediate eruption, subsequent starvation, and disease reached an estimated 71,000 people, the deadliest volcanic disaster in recorded history, most of them on Sumbawa, Lombok, and Bali. The stratospheric aerosol veil injected into the global atmosphere by Tambora's 1815 eruption set in motion a cascade of climatic consequences so profound that the following year entered history under the haunting designation, 1816, the year without a summer. Across the northern hemisphere, average temperatures plummeted. In New England, frosts occurred in every month of the summer of 1816. In June, snow fell across parts of New York and New England. Farmers who had planted crops watched them die in unprecedented cold snaps. Grain harvests failed across Europe, triggering food shortages that spiraled into famine, civil unrest, and mass migration. In Switzerland, the summer of 1816 was so cold and wet that two young English visitors, the poet Percy Bysshe Shelley and his companion Mary Godwin, spent their holiday largely confined indoors at the Villa Diodati on Lake Geneva, entertaining themselves with ghost stories. From that rain-darkened summer, Mary Godwin, soon to be Mary Shelley, composed the tale of a scientist who creates a monster, a novel born, in a very real sense, from the shadow of a volcano half a world away. Among the most visually arresting and scientifically fascinating phenomena associated with volcanic eruptions is the dramatic electrical discharge known as volcanic lightning, a spectacle of crackling energy threading through towering columns of ash, gas, and volcanic debris with an eerie, otherworldly luminescence. Unlike the lightning generated in meteorological thunderstorms, which arises primarily from the collision and separation of ice crystals and water droplets within cumulonimbus clouds, volcanic lightning is generated through multiple distinct mechanisms operating simultaneously within the eruption column. The most immediate of these involves triboelectric charging, the buildup of static electricity through the friction of ash particles and rock fragments colliding at high velocities as they are ejected from the volcanic vent. A second mechanism involves the fragmentation of magma itself during explosive eruptions, a process that can generate electrical charges at the point of fragmentation. A third process relates to the ionization of gases within the superheated eruption column. The resulting lightning can strike within the column, arc laterally across its surface, or discharge downward to the ground, producing bolts of extraordinary beauty that photographers and volcanologists alike regard with reverent fascination and considerable personal danger. The scientific study of volcanic lightning has advanced dramatically in recent decades through the deployment of lightning mapping arrays, infrasound detectors, and high-speed camera systems capable of resolving individual lightning strokes within eruption columns that traditional observational methods could not penetrate. Researchers have identified several distinct phases of volcanic lightning, each occurring at different stages of an eruption and at different altitudes within the column. Near-vent lightning, occurring within seconds to minutes of an explosive burst, appears to be dominated by triboelectric and fragmentation charging mechanisms. More distal and vertically extensive lightning higher within the eruption column increasingly resembles meteorological lightning, as ice formation and hydrometeor interactions contribute to charge separation at higher altitudes where the column cools and interacts with ambient atmospheric moisture. The ratio and character of volcanic lightning has been proposed as a potential monitoring tool. Changes in lightning frequency and spatial distribution correlate with changes in eruption intensity and column height in ways that could provide real-time diagnostic information for volcanologists attempting to assess eruption evolution from safe distances. Some researchers dream of instrumented aerostats that could sample the very heart of lightning-bearing eruption columns. Of all the mortal expressions of a volcano's fury, perhaps none is more instantly fatal and terrifyingly beautiful than the pyroclastic density current, a turbulent, ground-hugging avalanche of volcanic gases, ash, pumice fragments, and rock debris that can surge from a collapsing eruption column or from the explosive disintegration of a lava dome at speeds exceeding 300 kilometers per hour and temperatures ranging from 300 to 800 degrees Celsius. The term pyroclastic derives from the Greek for fire and broken, and nothing more accurately captures the nature of these flows. They are living incandescents in motion, capable of flowing around topographic obstacles, surging up and over ridgelines, and extending dozens of kilometers from their source before their thermal energy finally dissipates. The survivors of documented pyroclastic flow encounters are extraordinarily rare. The heat, the pressure wave that precedes the flow itself, and the complete displacement of breathable air by volcanic gas combine to create a lethality that is effectively absolute. At Pompeii, at Martinique's Saint-Pierre in 1902, at Montserrat in 1997, pyroclastic flows have written history in ash and silence. The volcano's capacity for destruction does not end when its eruption ceases, for water and volcanic debris combine in the landscape long after the eruption's cessation to produce one of the most insidiously dangerous of all volcanic hazards, the lahar. A lahar is a volcanic mudflow, a rapid slurry of water and volcanic material that flows down river valleys from volcanic slopes with the viscosity of wet concrete and the force of a freight train. Lahars form when heavy rainfall mobilizes loose volcanic deposits, when pyroclastic flows melt glaciers and snowfields in moments, or when crater lakes, sometimes containing vast volumes of acidic water, fail catastrophically. The Nevado del Ruiz eruption in Colombia in November 1985 produced lahars that traveled down river valleys at speeds of between 30 and 50 kilometers per hour, sweeping through the town of Armero while most of its 23,000 inhabitants slept, burying them beneath meters of volcanic mud in the course of a single devastating hour. The town of Armero, once a prosperous agricultural center, now exists only as an archaeological site beneath a mudflat, a testament to the hazard that geologists had warned local authorities about with increasing urgency in the weeks before the eruption. There is a category of volcanic events so large, so transformative, and so geologically consequential that it transcends the conventional imagery of erupting mountains and lava rivers, the supervolcanic caldera-forming eruption. A caldera is not a volcanic crater formed by explosion but rather a vast depression, often tens of kilometers in diameter, formed when the underlying magma chamber is catastrophically emptied during an eruption, causing the overlying roof of rock to collapse inward under its own weight. The resulting topographic feature can be mistaken from the ground for a natural valley or lake basin. The volcanic nature of Yellowstone's caldera, for instance, was not fully appreciated until aerial photography and geological mapping revealed its true dimensions. Caldera-forming eruptions expel volumes of magma measured in hundreds to thousands of cubic kilometers, blanketing entire continents in ash and injecting climatic quantities of aerosols into the stratosphere. The Toba supereruption approximately 74,000 years ago in what is now Sumatra, Indonesia, may have reduced global temperatures by 15 degrees Celsius for years, potentially reducing the global human population to a genetic bottleneck of perhaps 10,000 individuals or fewer. Beneath the extraordinary geothermal spectacle of Yellowstone National Park, its prismatic hot springs, its roaring geysers, its bubbling mud pots, and its steaming fumarolic fields, lies one of the most closely monitored and scientifically scrutinized magmatic systems on Earth, the Yellowstone supervolcano. The Yellowstone hotspot has generated 3 massive caldera-forming eruptions over the past 2.1 million years, at approximately 2.1 million, 1.3 million, and 640,000 years ago, each producing eruptions of continental significance. The most recent of these events, the Lava Creek Tuff eruption, ejected approximately 1,000 cubic kilometers of volcanic material and formed the caldera that now underlies much of Yellowstone Lake and the central portion of the national park. Today, a partially molten magmatic body, imaged by seismic tomography as a complex, partially crystallized mush zone, extends from roughly 8 to 48 kilometers depth, with a shallower hydrothermal system above it responsible for the park's extraordinary geothermal features. The ground surface of the caldera rises and falls measurably each year, a breathing observable only through precision GPS measurements. Not all volcanoes aspire to the dramatic symmetry of the stratovolcano or the catastrophic implosion of the caldera. Some, built patiently over millions of years from the accumulated flows of low-viscosity basaltic lava, spread themselves across the landscape in vast, gently sloping forms that geologists affectionately describe as shield volcanoes, named for their resemblance to a warrior's shield laid flat upon the ground. Mauna Loa and Mauna Kea in Hawaii are perhaps the world's most iconic shield volcanoes, and when measured from their base on the ocean floor rather than from sea level, they are the tallest mountains on Earth. Mauna Kea rises approximately 10,200 meters from its oceanic base, exceeding Everest's height above sea level by over a kilometer. Shield volcanoes grow in broad, low-gradient mounds because their low-viscosity lavas travel great distances before solidifying, each flow adding a thin layer to an ever-widening edifice. The eruptions of shield volcanoes are rarely explosive, lava fountains rather than Plinian columns characterize their most energetic moments, and their flows, while relentless and ultimately unstoppable, usually advance slowly enough to permit evacuation. Hawaii's volcanic landscape offers an extraordinary classroom for understanding the diverse textural and morphological vocabulary of basaltic lava flows. 2 Hawaiian language terms have entered the global scientific lexicon to describe the 2 fundamental surface textures that basaltic lava produces as it cools and solidifies. Pahiho, pronounced pahihoi, is the smooth, ropey, billowed lava whose surface forms as a thin, rapidly cooling skin wrinkles and folds over the still-flowing interior like slow-motion taffy. Pronounced ya, a name that evokes the sound one might make walking barefoot across it, is the rough, clinkery, jagged lava whose surface forms when gas-rich lava flows more turbulently and its cooling outer layer is broken into sharp fragments. The same eruption can produce both lava types, depending on the local slope gradient, flow velocity, and lava supply rate. Within Pahoehoe flows, lava tubes form as the surface solidifies while the interior continues to drain, creating hollow conduits that can carry lava tens of kilometers from the vent, insulating the melt and allowing it to travel far beyond where open channel flows would have cooled and solidified. The lava tubes of Hawaii, the Canary Islands, Iceland, and other basaltic volcanic terrains are not merely geological curiosities. They represent some of the most unusual and biologically fascinating habitats on Earth. Once the eruption that created them has ceased and the residual heat has dissipated over decades and centuries, these dark, humid, thermally stable tunnels are colonized by extraordinarily specialized communities of organisms that have adapted to life in permanent darkness, limited nutrient availability, and remarkably constant environmental conditions. Biologists studying lava tube ecosystems have documented diverse assemblages of invertebrates, cave-adapted insects, spiders, millipedes, and isopods that have often developed populations genetically isolated from surface relatives since the tubes formed. Some lava tube organisms have lost eyes entirely over evolutionary time, replacing them with enhanced non-visual sensory systems. The geochemistry of lava tube environments also supports chemolithotrophic microbial communities, bacteria that derive energy from the oxidation of minerals in the basaltic rock walls, forming the base of a food web that depends not on photosynthesis but on the chemical energy locked in volcanic minerals. These microbial films have been proposed as analogues for potential life in subsurface environments on other worlds. In February 1977, a team of geologists aboard the deep-sea submersible Alvin descended to the seafloor along the Galapagos Rift in the eastern Pacific Ocean, expecting to survey a barren, cold, sediment-covered landscape in the dead zone of the deep ocean. What they found instead was one of the most revolutionary biological discoveries of the 20th century. Thriving, unexpectedly dense and diverse communities of life clustered around warm-water hydrothermal vents on the volcanic seafloor, communities that existed in complete independence from sunlight and photosynthesis. These vent communities, sustained by chemosynthesis, the biological conversion of chemical energy from hydrogen sulfide and other reduced compounds into organic matter, shattered the assumption that all life on Earth ultimately depends on solar energy. Giant tube worms over 2 meters in length, ghostly pale crabs, clusters of mussels and clams, and shimmering schools of fish crowded around the warm, mineral-rich vent fluids in abundances that seemed impossible in the nutrient desert of the deep sea. The discovery expanded our conception of the biosphere and our understanding of where life can exist, with profound implications for the search for life elsewhere in the solar system. 2 years after the initial discovery of warm hydrothermal vents, researchers encountered the most spectacular and extreme expression of seafloor volcanism and its biological consequences: the black smoker. Black smokers are high-temperature hydrothermal vents that emit superheated, mineral-laden fluids at temperatures exceeding 350 degrees Celsius, well above the boiling point of water at sea level, but maintained in liquid state by the immense pressures of the deep ocean. The characteristic dark plumes that give these structures their name are composed of tiny particles of iron, zinc, copper, and other metal sulfides that precipitate instantaneously when the superheated vent fluid contacts the cold surrounding seawater. Over time, these mineral precipitates build towering chimney structures, some reaching heights of several stories, through which the black fluids continue to surge in a perpetual mineral fountaining. Surrounding these extreme thermal environments, thermophilic and hyperthermophilic microorganisms, heat-loving bacteria and archaea that thrive at temperatures lethal to all other known life, form the base of vent food webs. Some of these organisms can survive and metabolize at temperatures approaching 120 degrees Celsius, stretching the known limits of biology toward conditions that seem more appropriate to a geological than a biological realm. The volcanic vent environments of both the deep sea and terrestrial hot springs have become among the most productive hunting grounds for the emerging science of astrobiology, not merely because of the exotic organisms they harbor, but because of what those organisms reveal about the fundamental plasticity of life as a phenomenon. at the Kamchatka hot springs of Russia, in the boiling mud pots of Yellowstone, in the steaming thermal lakes of Iceland and New Zealand, microbiologists have catalogued an extraordinary menagerie of extremophilic organisms, creatures of the archaea domain in particular, that have evolved biochemical machinery of remarkable ingenuity to function under conditions of heat, acidity, alkalinity, pressure, and chemical toxicity that would destroy the proteins and genetic material of all other known life. The enzymes of thermophilic organisms, evolved to remain stable and functional at extreme temperatures, have found profound biotechnological applications. The polymerase chain reaction technique, the foundation of modern molecular biology and genetic diagnostics, relies on a heat-stable DNA polymerase originally isolated from the thermophilic bacterium Thermus aquaticus, discovered in a Yellowstone hot spring in 1966. Life, it seems, has found a home in the very fires of the Earth. Among the most otherworldly environments on Earth's surface are the hyperacid crater lakes that occupy the summit calderas of certain volcanoes, bodies of water so saturated with volcanic acids that they achieve pH values close to zero, making them among the most corrosive natural liquids known. The crater lake of Kawah Ijen volcano in East Java, Indonesia, contains approximately 200 million cubic liters of hydrochloric acid solution so concentrated that it dissolves the clothing and skin of those unfortunate enough to fall into it, and corrodes metal equipment left in contact with the water in a matter of hours. Yet even in these apparently impossible environments, life has been found. Microorganisms of the Acidithiobacillus genus and related acid-tolerant archaea are capable of surviving and metabolizing in pH conditions approaching zero, thriving on the oxidation of sulfur and iron compounds dissolved in the volcanic acid. The existence of microbial communities in these extreme environments has expanded our understanding of the outer boundaries of the biosphere and reinforced the hypothesis that wherever liquid water exists on Earth, life has found a way to colonize it, a principle with profound implications for the search for life in the acidic clouds of Venus. Between the dramatic spectacle of an active lava flow and the quiet dormancy of a resting volcanic edifice lies a whole vocabulary of gentler volcanic expressions, the fumaroles and solfataras that whisper of subsurface heat and chemical activity through their perpetual exhalations. A fumarole is simply a vent in the Earth's surface from which volcanic gases, primarily water vapor, but often including carbon dioxide, sulfur dioxide, hydrogen sulfide, and a cocktail of more exotic compounds, emerge in continuous or episodic plumes. The Solfatara field near Pozzuoli in the Campi Flegrei caldera system west of Naples takes its name from the sulfurous odor of its emissions, and indeed the English word, solfatara, is now used generically for any fumarolic field where sulfurous gases dominate. These gaseous exhalations deposit mineral crusts of extraordinary chromatic variety around their vents, brilliant yellows of native sulfur, oranges and reds of iron oxides, whites of aluminum sulfate and other evaporite minerals, creating geological palettes of accidental beauty. The composition of fumarolic gases provides volcanologists with a continuous chemical window into the magmatic system below, and changes in gas ratios can serve as early warning indicators of building eruptive activity. The invisible chemistry of volcanic gases constitutes one of the most powerful and nuanced tools available to volcanologists attempting to peer into the inaccessible interior of a volcanic system and interpret the intentions of the magma that lies within. Magma contains dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide, that remain in solution under the high pressures of the deep magma chamber but exsolve progressively as the magma rises toward the surface and pressure decreases. By monitoring the flux and composition of gases escaping from a volcano's fumaroles, summit vents, and flanks, scientists can infer changes in the depth of the degassing magma, the rate of its ascent, and the degree of connectivity between deep and shallow parts of the system. The ratio of sulfur dioxide to carbon dioxide is particularly informative. Carbon dioxide exsolves at greater depths than sulfur dioxide, so an increasing CO2 to SO2 ratio in volcanic emissions can indicate the arrival of fresh, volatile-rich magma rising from depth into a previously stagnant system. This chemical sentinel function has contributed to successful eruption forecasts at several volcanoes, including the 1991 eruption of Mount Pinatubo in the Philippines, one of the most successful volcanic hazard mitigation stories of the 20th century. The eruption of Mount Pinatubo in the Philippines in June 1991 stands as one of the most consequential volcanic events of the late 20th century and, simultaneously, as one of the greatest successes in the history of volcanic hazard mitigation. Pinatubo had been dormant for approximately 500 years when increased seismicity, ground deformation, and escalating gas emissions in early 1991 alerted the Philippine Institute of Volcanology and Seismology and United States Geological Survey scientists to the possibility of a major eruption. Their monitoring campaign, deploying seismometers, tilt meters, GPS stations, and gas analyzers around the volcanic edifice, provided sufficient advance warning for the evacuation of over 200,000 people from the danger zone. The eruption on June 15 was the second largest of the 20th century, ejecting approximately 10 cubic kilometers of pyroclastic material and sending a Plinian column 24 kilometers into the stratosphere. The coincidental passage of Typhoon Yunya added rain to the ash fall, causing catastrophic roof collapses. Despite the eruption's violence, the evacuations reduced the death toll to approximately 800 lives, a figure that, in the absence of monitoring and warning, might have reached many tens of thousands. The language spoken most fluently between a restless volcano and the scientists who attend to it is the language of seismicity, the ground vibrations, tremors, and earthquakes generated by the physical and chemical processes occurring within the volcanic edifice and its underlying plumbing system. Volcanologists distinguish between several characteristic seismic signatures, each carrying diagnostic information about the processes generating it. Volcano-tectonic earthquakes, with their sharp high-frequency waveforms, indicate the brittle fracturing of rock under stress, often the opening of new fractures as magma forces its way upward. Long-period seismic events, with their lower frequencies and emergent onsets, are generated by the oscillation of fluid-filled cracks as magma or hydrothermal fluids move through them, producing resonant vibrations analogous to the sound of a struck tuning fork. Harmonic tremor, a sustained, nearly continuous low-frequency seismic signal, is often interpreted as magma or fluids flowing through conduits in an ongoing, steady-state manner. The timing, frequency, depth, and migration patterns of these seismic signals allow skilled volcanologists to construct evolving pictures of magma movement through the crust, often providing days or weeks of warning before eruptions reach the surface. The surface of a volcano is not passive geography. It is a living topographic expression of the pressures and temperatures changing within the volcanic edifice beneath it. As magma accumulates in a shallow magma chamber, the overlying crust inflates measurably, a process that tilts inclinometers, extends the distances between GPS benchmarks, and produces surface deformation patterns detectable from space by radar interferometry. The technique of interferometric synthetic aperture radar, or INSAR, has revolutionized volcano monitoring by allowing scientists to measure ground deformation across entire volcanic edifices with centimeter-level precision using satellite radar signals, creating deformation maps that reveal the location, volume, and pressure changes within shallow magmatic bodies as they evolve over time. Conversely, when magma withdraws from a shallow chamber, either erupting or draining deeper, the overlying crust deflates, and this subsidence is equally detectable. At Kilauea in Hawaii, Sentinel satellites captured the extraordinary deflation of the summit caldera in real time during the 2018 eruption event, documenting the collapse of the Halemaumau crater floor in a series of incremental downward steps as the shallow magma body drained to feed the eruption 17 kilometers away on the lower East Rift Zone. The eruption events that unfolded at Kilauea Volcano on the island of Hawaii during the spring and summer of 2018 offered the global scientific community an extraordinary real-time window into the complex, interconnected behavior of a volcanic system responding dynamically to the withdrawal of its magmatic heart. In early May 2018, after months of elevated seismicity, the floor of the Po vent, which had been erupting nearly continuously since 1983, making it one of the longest-lived rift eruptions in historical record, collapsed abruptly, sending a pulse of pressure eastward along the lower East Rift Zone. Within days, fresh eruption fissures had opened in the residential neighborhood of Leilani Estates, sending rivers of extremely fluid, fast-moving lava across subdivisions and into the ocean. Meanwhile, the emptying of the shallow summit magma chamber produced a series of magnitude 5 earthquakes and incremental collapses of the Halemaumau crater floor, deepening it by hundreds of meters over weeks of dramatic subsidence. The eruption destroyed approximately 700 homes and covered some 13 square kilometers of the lower East Rift zone in new lava, while simultaneously adding new land as lava deltas expanded the island's southeastern shoreline into the sea. Iceland occupies a unique geological position that makes it one of the world's most volcanically active and geologically instructive nations. It sits astride the Mid-Atlantic Ridge, the divergent plate boundary where the Eurasian and North American tectonic plates are separating, while simultaneously being underlain by the Iceland mantle plume, a deep hotspot that has supplied anomalously large volumes of magma to the ridge for millions of years. This coincidence of divergent boundary and hotspot volcanism has built Iceland itself. The island is composed entirely of volcanic rock, accumulated over roughly 20 million years of eruptive activity, and new volcanic rock continues to be created at its surface today. Iceland averages a volcanic eruption approximately every 4 to 5 years, and its volcanic systems include some of the most productive on Earth. The 2010 eruption of Age of Geological, whose name became internationally famous primarily for the difficulty non-Icelandic speakers experienced in pronouncing it, disrupted European air travel for weeks when its ash plumes spread across the continent, providing a vivid demonstration of how volcanic events in one location can have economic and logistical consequences of continental reach. Among the most consequential volcanic eruptions in the historical record, yet among the least celebrated in popular memory, was the Laki Fissure eruption in Iceland in 1783 and 1784. Along a fissure system approximately 27 kilometers long, thousands of individual vents opened in rapid succession, collectively disgorging approximately 14 cubic kilometers of basaltic lava, one of the largest lava flow eruptions since the Ice Age, over the course of 8 months. More significantly, the eruption released an estimated 120 million tons of sulfur dioxide into the lower atmosphere, producing a persistent haze known in Icelandic as the Mjöharindin, the mist hardship, that spread across Europe and North America. The acid haze damaged crops across the northern hemisphere, contributing to famine conditions. In Iceland itself, the eruption was catastrophic. Fluorine released with the volcanic gases poisoned pastures and water supplies, killing approximately 50 to 80% of the island's livestock and leading to the death of approximately 20% of the human population in the subsequent famine. In Europe, the resulting crop failures and climatic disruption may have contributed to the social tensions that preceded the French Revolution of 1789. The concept of volcanism has been profoundly expanded and reimagined since the space age delivered instruments to the distant reaches of the solar system and returned evidence of volcanic activity on worlds where the erupting material is not silicate magma but ice, liquid water, ammonia, methane, or nitrogen, eruptions so cold that we have coined the term cryovolcanism to encompass this alien category of geological expression. On these frigid worlds, where surface temperatures plunge hundreds of degrees below zero, the volatiles that we encounter as atmospheric gases or surface liquids on Earth become solid ice. And it is the melting or pressurization of these ices under subsurface heat that drives cryovolcanic eruptions to the surface. The discovery of cryovolcanism has transformed planetary science by demonstrating that the geological and perhaps biological processes enabled by volcanism, including the redistribution of chemical compounds, the maintenance of subsurface liquid reservoirs, and the potential delivery of energy and nutrients to otherwise frozen environments, are not limited to the warm inner solar system but may operate wherever sufficient internal heat exists within an icy world. Jupiter's innermost large moon, Io, presents a spectacle of volcanic activity so extreme, so relentless, and so visually dramatic that it occupies a category entirely apart from anything else in the observable solar system. Discovered by Galileo Galilei in 1610, Io was not recognized as a volcanically active world until Voyager 1's 1979 flyby, when navigation engineer Linda Morabito noticed a large umbrella-shaped plume extending from the moon's surface in an overexposed image taken for navigation purposes, the first active volcano ever observed beyond Earth. Io's volcanic activity is driven not by radioactive decay or residual heat from formation but by tidal heating. The gravitational forces of Jupiter and the other Galilean moons, Europa, Ganymede, and Callisto, flex and squeeze Io's interior in a continuously varying pattern as the moon orbits, generating internal heat through tidal friction on a scale that has maintained Io in a state of perpetual volcanic paroxysm for the entirety of its existence. The result is a moon whose surface is continuously resurfaced by lava flows and volcanic deposits at rates that completely erase impact craters, giving Io the youngest and most dynamically active surface in the solar system, a world perpetually consuming and recreating itself. The volcanoes of Io operate at scales and temperatures that dwarf anything in Earth's geological experience. The hottest volcanic eruptions ever measured in the solar system have been recorded on Io, with some lava flows achieving temperatures exceeding 1600 degrees Celsius, significantly hotter than any known contemporary terrestrial eruption, suggesting that Io's lavas may be ultramafic komatiite-like compositions last erupted on Earth during the Archean Eon more than 2.5 billion years ago. The volcanic plumes of Io reach heights of up to 500 kilometers above the surface, driven by the explosive boiling of sulfur dioxide frost when it contacts hot lava, and deposit ring-shaped aureoles of sulfur and sulfur dioxide snow across vast regions of the moon's surface. The volcanic calderas of Io are among the largest in the solar system, with some exceeding 200 kilometers in diameter. Loki Patera, one of the largest volcanic features on Io, is a lava lake over 200 kilometers across whose surface periodically overturns in a wave of resurfacing that circles the lake over a period of approximately 500 days, a volcanic clock of extraordinary regularity, visible from Earth with large telescopes. Saturn's small moon Enceladus has become one of the most extraordinary objects of scientific fascination in the entire solar system, not because of its spectacular geology, though that alone would justify wonder, but because of what that geology implies about the possibility of life in the outer solar system. Beneath Enceladus's pristine white icy surface, maintained at temperatures around -190 degrees Celsius, lies a global subsurface ocean of liquid water kept from freezing by the tidal heating generated by Saturn's gravitational interactions with the Moon. Near the south pole of Enceladus, a system of parallel surface fractures known as the Tiger Stripes vents plumes of water vapor and ice particles into space at velocities sufficient to escape the Moon's feeble gravity and contribute to Saturn's E-ring. The Cassini spacecraft, which studied the Saturn system from 2004 to 2017, flew directly through these plumes on multiple occasions and detected the presence of molecular hydrogen, silica nanoparticles, organic compounds, and salts, a chemical fingerprint consistent with ongoing hydrothermal reactions between liquid water and warm rocky seafloor, conditions remarkably similar to the hydrothermal vent environments on Earth where life first may have emerged. Jupiter's moon Europa and Saturn's moon Titan both harbor evidence of cryovolcanic or related subsurface processes that have captivated planetary scientists and astrobiologists alike, each presenting a distinct chemical and thermal scenario for the potential generation and sustenance of life beneath an icy exterior. Europa's subsurface ocean, larger in volume than all of Earth's oceans combined, is maintained in liquid state by the same tidal heating mechanism that powers Io's dramatic volcanic activity, and the evidence for hydrothermal activity on Europa's ocean floor, while less direct than on Enceladus, is supported by magnetic field measurements, surface geology, and thermal modeling. Titan, with its thick nitrogen and methane atmosphere and its surface lakes and rivers of liquid methane and ethane, occupies an even stranger niche, a world where organic chemistry proceeds in cryogenic conditions, and where methane cycles through the atmosphere, surface, and subsurface in ways that analog the water cycle on Earth. Titan's cryovolcanism, if it exists as some researchers suggest, may involve eruptions of liquid water-ammonia mixtures from a subsurface ocean, creating temporary surface environments of exotic chemistry before refreezing. Neptune's largest moon, Triton, the only large moon in the solar system that orbits in the retrograde direction, backward relative to its planet's rotation, suggesting it was captured from the outer solar system rather than formed in place, presents one of the most unexpected cryovolcanic phenomena discovered by robotic exploration. During Voyager 2's fleeting 1989 flyby, cameras revealed dark streaks on Triton's nitrogen ice surface extending downwind for hundreds of kilometers, and active geyser-like plumes of dark material venting from the south polar cap. These plumes are thought to be driven by the sublimation of nitrogen ice. Solar radiation, though extraordinarily weak at Neptune's distance of 30 astronomical units from the Sun, penetrates the transparent nitrogen ice and warms a darker layer beneath, generating nitrogen gas pressure that eventually erupts through the ice cap in a dark plume of gas and entrained dark organic particles. The extreme cold of Triton's surface, approximately -235 degrees Celsius, one of the coldest surfaces in the solar system, makes this cryovolcanic activity all the more remarkable, demonstrating that geological dynamism can persist even at the threshold of absolute zero. The New Horizons mission's flyby of Pluto in July 2015 returned images of extraordinary geological complexity from this distant world, including possible evidence of cryovolcanic activity in the form of massive dome-like structures in the southern hemisphere that could represent the solidified remnants of cryovolcanic eruptions of ice and volatile compounds. Wright Mons and Picard Mons, two of the largest of these structures, each rise several kilometers above the surrounding terrain and display central depressions consistent with volcanic edifices built from repeated eruptions, though the debate about their origin continues among planetary scientists. The discovery that Pluto, long presumed to be a geologically dead, frozen relic, displays evidence of recent geological activity has reinforced the emerging consensus that small, cold, icy bodies in the outer solar system retain more internal heat and geological vigor than classical planetary science predicted. This has important implications for the frequency of habitable subsurface environments throughout the solar system and beyond, suggesting that the zone of potential geological and perhaps biological activity extends far beyond the conventional habitable zone defined by liquid water stability on planetary surfaces. Long before Western science developed the vocabulary of plate tectonics, magma chambers, and pyroclastic density currents, the peoples who lived in the shadow of volcanoes wove the fire mountains into their spiritual and cosmological frameworks in ways that reveal the profound psychological and cultural impact of living alongside one of nature's most dramatic forces. In the Hawaiian tradition, volcanic activity is understood as the expression of Pele, the goddess of volcanoes, fire, and creation, who is said to reside in the active lava lakes of Kilauea and to walk the land as a beautiful young woman or a withered old crone before eruptions manifest. The flows that advance across the landscape and consume homes and forests are not destruction in the Hawaiian cultural framework, but the movement of a divine being reshaping and recreating the land. The islands themselves are understood as the body of Pele, built by her creative volcanic power from the ocean floor. This perspective has profoundly influenced contemporary Hawaiian relationships with volcanic hazard, creating a cultural context in which the loss of property to lava flows carries a spiritual significance and an acceptance that sits alongside, and sometimes in tension with, the Western hazard management framework imposed by state and federal emergency agencies. The Roman god Vulcan, Hephaestus in the Greek tradition, stood at the intersection of fire, craft, and volcanic power in Mediterranean religious imagination, lending his name not only to the modern scientific term volcano, but to the entire conceptual vocabulary by which Western civilization first understood and categorized fire mountains. Vulcan was the divine smith, the lame craftsman who labored in his subterranean forge beneath the volcanic islands to the north of Sicily, the Aeolian Islands, which include the perennially active Stromboli and the island of Volcano itself, hammering out the armor of gods and heroes in a celestial workshop that the Romans believed was the physical source of the fire and smoke they observed emanating from these islands. The association of volcanic fire with divine craftsmanship and creative intelligence, rather than with destruction alone, reflects an ancient intuition that the energies emerging from the Earth's interior are generative as well as destructive, capable of forging the instruments of civilization as well as annihilating its achievements. This dual nature of volcanic fire, creative and destructive simultaneously, runs through volcanic mythology across cultures and continents with remarkable consistency. The volcanic landscapes of New Zealand, Aotearoa, are woven into the origin stories and spiritual geography of the Maori people with an intimacy that reflects millennia of coexistence with geothermally active terrain. The Taupo volcanic zone, which includes the world's most productive rhyolitic volcanic system, is regarded in Maori tradition as a place of spiritual power and significance, with many of its geothermal features, lakes, and volcanoes bearing names that encode histories, genealogies, and sacred narratives. Mount Taranaki, the imposing stratovolcano on the North Island's west coast, is understood as a living ancestor, a former inhabitant of the central volcanic plateau who departed in grief and anger after losing a battle with the volcanic mountains of the Taupo region, his passage across the landscape leaving the Hoanganui River Valley. In Philippine mythology, the volcano Mayon, renowned for its near-perfect conical form, is associated with the legend of Magayan, a beautiful woman whose tragic death gave the mountain its name. Across the Pacific, volcanic mountains are almost universally regarded not as geological features but as living presences, ancestors, deities, or spiritual entities whose moods manifest as eruptions and whose tranquility sustains the communities at their feet. Mount Fuji, the elegant stratovolcano that rises to 3,776 meters above Japan's Honshu Island and has long served as the nation's most iconic geographical and spiritual symbol, occupies a position in Japanese culture that transcends mere landscape to become something approaching a living philosophical statement about the relationship between beauty, impermanence, and power. Fuji's last eruption occurred in 1707, the Hoi eruption, which deposited ash across Edo, the city now known as Tokyo, yet the mountain's dormant majesty continues to attract millions of pilgrims and tourists annually to its summit, where the crater of a volcano whose fires have not been extinguished but merely resting can be contemplated in the same breath as the sunrise. The Ainu people of Hokkaido and the indigenous communities of Kyushu and the Ryukyu Islands maintain their own volcanic mythologies rooted in direct experience of their respective volcanic landscapes. In Japan's cultural imagination, Fuji-san embodies the Buddhist concept of impermanence, mano no aware, the awareness that all beauty is transient, all solidity illusory, all peaks eventually destined to collapse into the caldera that awaits beneath every volcano's deceptive summit symmetry. The volcanic landscapes of the Americas, from the Cascade Range of the Pacific Northwest through the volcanic highlands of Mexico and Central America to the Andes of South America, have been deeply embedded in the mythologies and cosmologies of indigenous peoples for thousands of years of continuous habitation. The Aztec pantheon included Popocatépetl and Iztaccíhuatl, the Smoking Mountain and the White Woman, among its most sacred geographical and spiritual figures, their origin explained through a tale of tragic love between a warrior and a princess. In the oral traditions of the Klamath and Modoc peoples of what is now Oregon, the catastrophic eruption and collapse of Mount Mazama approximately 7,700 years ago, the event that created Crater Lake, was preserved across millennia in narrative form as a battle between the sky deity Leo and the underworld deity Skell, witnessed and survived by the people's ancestors. Geological evidence confirms that this oral tradition preserved an accurate, if mythologized, memory of one of the largest volcanic eruptions in North America since the end of the Ice Age, demonstrating the extraordinary capacity of oral tradition to transmit geological knowledge across hundreds of generations of storytelling. The archetypal image of a volcano in the global imagination, a steep, symmetrical cone of snow-capped beauty, wreathed in a wisp of perpetual vapor, rising dramatically above a surrounding landscape, corresponds to the geological form known as the stratovolcano or composite volcano. These structures are built over tens of thousands to hundreds of thousands of years through the alternating deposition of lava flows, pyroclastic fall deposits, and pyroclastic flow deposits, each eruption adding new material to the edifice while erosion and gravitational collapse simultaneously work to diminish it. The characteristic steep slopes of stratovolcanoes, typically between 20 and 30 degrees near the summit, reflect the high viscosity of the andesitic to dacitic lavas that predominantly construct them, These lavas cannot flow far from the vent before solidifying, stacking up near the summit to produce the elegant symmetrical cone. Yet this same high viscosity that creates the volcano's aesthetic grandeur also stores the energy for its most violent eruptions. When viscous, gas-rich magma cannot release its dissolved gases gradually, the pressure builds to the explosive release that produces the Plinian columns and pyroclastic flows that make stratovolcanoes the most hazardous category of volcanic edifice for human populations. The geological record reveals that volcanic edifices are not permanent monuments but inherently unstable structures subject to catastrophic failure, slope collapses of enormous volume that generate what are known as debris avalanches and, when they reach the sea, oceanic tsunamis of devastating potential. The sector collapse of Mount St. Helens on May 18, 1980, in which the entire north flank of the volcano slid away in the largest landslide in recorded history, a volume of approximately 2.8 cubic kilometers of rock, provided the first modern scientific documentation of volcanic flank failure. The collapse depressurized the volcanic system instantly, releasing the built-up volcanic gases in a lateral blast that devastated an area of approximately 600 square kilometers to the north of the volcano. The Hawaiian Islands, despite their gentle volcanic character, carry the scars of some of the largest debris avalanches in the geological record. The flanks of Mauna Loa have collapsed multiple times in its history, generating avalanches that traveled hundreds of kilometers across the ocean floor and produced tsunamis that reshaped coastlines around the Pacific Basin. The Canary Islands, built on similar oceanic hotspot foundations, are considered particularly susceptible to future flank collapses by some researchers. The eruption of Mount St. Helens in Washington state on May 18, 1980, stands as the most intensively studied and documented volcanic eruption in the history of North American geology, a watershed event that transformed volcanology from a largely descriptive science into one equipped with real-time monitoring, quantitative modeling, and vastly improved eruption forecasting capabilities. The eruption had been preceded by 6 weeks of escalating seismic activity and ground deformation, including the growth of a cryptodome on the volcano's north flank that advanced the slope at rates visible to the naked eye in time-lapse photography. Despite clear warnings and an established exclusion zone, the precise timing of the eruption's catastrophic escalation on the morning of May 18th, triggered by a magnitude 5.1 earthquake that destabilized the bulging north flank, caught some people within range. 57 people perished, including volcanologist David Johnston at his monitoring post and innkeeper Harry Truman, who famously refused evacuation. The resulting eruption column rose 24 kilometers. The lateral blast, superheated to over 300 degrees Celsius, devastated over 550 square kilometers. The eruption remains a defining moment in both volcanic science and American cultural memory. The concept of a volcanic winter, a prolonged period of global cooling resulting from the injection of volcanic aerosols into the stratosphere, represents one of the most consequential intersections between Earth's geological interior and its climate system, and one of the most sobering reminders of how profoundly geological events can alter the conditions of life across the entire planet's surface. The mechanism is relatively straightforward. When a sufficiently large volcanic eruption injects sulfur dioxide gas into the stratosphere, the gas converts to sulfuric acid aerosol droplets that scatter incoming solar radiation back into space, reducing the amount of energy reaching the surface and driving global cooling. The magnitude of cooling depends on the quantity of aerosol produced, the latitude and altitude of injection, and atmospheric circulation patterns. The historical record reveals multiple instances of multi-year volcanic winters associated with major eruptions. The Toba eruption approximately 74,000 years ago may have triggered a cooling episode of a decade or more. The unknown eruption of approximately 536 CE produced a dust veil that darkened skies across the northern hemisphere for 18 months, triggering what historians have identified as the onset of one of the coldest periods of the last 2,000 years. The year 536 CE stands out in the historical record of both hemispheres as the beginning of one of the most severe environmental crises of the first millennium, a period of prolonged atmospheric dimming, summer cooling, and agricultural failure that Byzantine historian Procopius described as a mysterious light that the sun gave forth without brightness, like the moon, throughout the whole year. Chinese annals recorded a dry fog obscuring the sun. Peruvian ice cores preserve the chemical signature of a massive volcanic event. Scandinavian tree rings froze at their minimum width. The source of this catastrophic aerosol veil remained mysterious for decades, but ice core analysis of both Antarctic and Greenland ice has revealed the chemical fingerprint of a massive volcanic eruption at high northern latitudes, now tentatively identified as originating from a large eruption in Iceland or possibly from an Alaskan volcanic source around 536 CE, possibly followed by further eruptions in 540 and 547 CE. Historian Kyle Harper has argued that the resulting famines, economic disruption, and population stress created conditions favorable for the plague of Justinian, one of the first great pandemic events in recorded Western history, by weakening communities across the Mediterranean world. In the deepest perspective of Earth's history, volcanism has been not merely a local hazard or a geological spectacle but a fundamental architect of the planetary conditions that make life possible. The secondary atmosphere of Earth, the nitrogen and carbon dioxide-rich atmosphere that replaced the primordial hydrogen and helium atmosphere of the newly formed planet, was largely outgassed from the planet's interior through billions of years of volcanic activity. Water vapor, carbon dioxide, nitrogen, and sulfur compounds vented from the early Earth's abundant volcanism condensed and accumulated to form the oceans and atmosphere that became the cradle of life. The carbonate-silicate cycle, which regulates Earth's long-term carbon dioxide concentration and keeps the climate within habitable bounds over geological timescales, depends critically on volcanic outgassing to replenish atmospheric CO2 that is continuously removed by chemical weathering and biological carbon fixation. Without the steady geological heartbeat of volcanism returning carbon to the atmosphere, the weathering pump would eventually strip the atmosphere of its greenhouse gases, and Earth's surface would freeze to temperatures incompatible with life. In the most profound sense, we exist because our planet has never stopped being volcanically alive. Among the most paradoxical aspects of volcanic landscapes is the relationship between the destruction that volcanoes periodically visit upon their surroundings and the extraordinary fertility that volcanic soils develop in the intervals between eruptions. Volcanic rocks, basalts, andesites, and rhyolites weather into soils unusually rich in the mineral nutrients required by plants: phosphorus, potassium, calcium, magnesium, and a suite of trace elements that are often depleted or unavailable in the old, deeply weathered soils of cratonic interiors. The fine-grained tephra that volcanic eruptions distribute across surrounding landscapes acts as a mineral supplement to existing soils, and the volcanic ash that devastates crops in the immediate aftermath of eruptions becomes a potent soil amendment within years to decades as it weathers to clay minerals and releases its mineral nutrients. The fertile volcanic soils of Java, Andesols, support some of the highest agricultural population densities in the world. The rich coffee-growing regions of Guatemala, Costa Rica, and Colombia owe their exceptional soil quality to volcanic geological heritage. The Sicilian hinterlands of Etna produce wine grapes of distinctive character from volcanic soils that have been cultivated for millennia, each vintage carrying a trace mineral memory of geological fire. Long before civilizations understood what volcanoes were, they were using volcanic products with sophisticated intentionality that shaped the trajectory of human cultural and technological evolution. Obsidian, the jet-black, naturally occurring volcanic glass formed when silica-rich lava cools too rapidly to allow crystal growth, was among the most valued raw materials in the prehistoric world, prized for its exceptional sharpness when fractured through careful knapping. A freshly struck obsidian flake can achieve a cutting edge approaching molecular thickness, sharper than modern surgical steel, and prehistoric peoples recognized and exploited this property for cutting tools, surgical instruments, projectile points, and ceremonial objects. The distinctive compositions of different obsidian sources, each volcanic flow producing obsidian with a unique chemical fingerprint determined by the magma's elemental proportions, allow archaeologists to trace the prehistoric distribution networks through which obsidian moved across landscapes and between communities, revealing trade routes that crossed mountain ranges and ocean stretches. Obsidian from sources in Anatolia has been found at sites across the ancient Middle East. Pacific Island obsidian was distributed across thousands of kilometers of ocean. The volcanic glass was, in its time, a global commodity. Volcanic tephra, the airfall deposits of ash and pumice ejected during explosive eruptions, has become one of the most powerful tools in the archaeological and paleoecological toolkit, serving as a precisely datable marker horizon that allows the correlation of stratigraphic sequences across vast distances and provides absolute time references for events recorded in lake sediments, peat bogs, ice cores, and archaeological excavations. The technique, known as tephrochronology, exploits the fact that each major volcanic eruption produces tephra with a distinctive chemical composition that geochemists can measure in the microscopic glass shards preserved in sediment archives, effectively barcoding each eruption and allowing individual tephra layers to be recognized wherever they are preserved. The Hekla 4 tephra from Iceland, deposited approximately 4,000 years ago, has been identified in peat deposits and lake sediments from Ireland to Scandinavia to Siberia, providing a synchronous time marker across the North Atlantic and adjacent regions that allows paleoecologists to compare the timing of environmental changes recorded at different sites with extraordinary precision. The combination of tephrochronology with other dating methods has transformed our ability to understand the tempo and synchronicity of past environmental and cultural changes. Volcanic islands, erupted from the ocean floor and rising above the sea surface as new land where no land has existed before, provide evolutionary biology with some of its most instructive natural experiments in colonization, adaptation, and speciation. When a new volcanic island breaks the ocean surface, it presents arriving organisms with an environment of profound ecological emptiness. Fresh, nutrient-poor volcanic rock, minimal soil, few if any resident competitors or predators, and an enormous selective opportunity for any organisms tough enough to survive the crossing and establish populations. The Galapagos Islands, which Charles Darwin visited in 1835 and whose organisms contributed critically to his developing theory of natural selection, owe their extraordinary biological legacy to their volcanic origin. Each island in the archipelago is a different age and a different volcanic composition, and their biological communities reflect millions of years of colonization from the South American mainland followed by evolutionary divergence under the distinct ecological conditions of each island. The Hawaiian Islands offer an even more dramatic example. The extreme isolation of the Hawaiian hotspot has produced one of the world's most spectacular examples of adaptive radiation, with a single ancestral colonizing lineage of finch-like birds diversifying into the extraordinary variety of forms now known as Hawaiian honey creepers. The economic dimensions of volcanism extend far beyond the agricultural fertility of volcanic soils into the domain of mineral wealth. For some of the most important metal deposits mined by human civilization were created by volcanic hydrothermal processes operating over millions of years in the geological past. When hot, metal-rich hydrothermal fluids associated with volcanic systems circulate through fractures in the crust and encounter changes in temperature, pressure, or chemistry, they deposit their dissolved metal loads as concentrated or bodies. The porphyry copper deposits of the Andes and the North American Cordillera that supply a significant fraction of the world's copper production. The gold-rich epithermal deposits associated with shallow volcanic systems in Nevada and elsewhere, and the massive sulfide deposits of ancient submarine volcanic systems that have been uplifted onto continents and mined for copper, zinc, and lead. The ancient mines of Cyprus, whose very name may derive from the Greek word for copper, Kypros, exploited massive sulfide ore bodies formed by hydrothermal systems on the floor of the ancient Tethys Ocean and contributed copper to the Bronze Age Mediterranean economy over thousands of years of continuous extraction. Volcanic hydrothermal systems, in the deep time of geology, created much of the metallic infrastructure of human civilization. Among the more surprising connections between volcanism and human material culture is the role of a specific type of ancient, deep-sourced volcanic eruption in delivering diamonds to the Earth's surface from depths at which they form under the immense pressures and temperatures of the mantle. Kimberlite pipes, named for the South African town of Kimberley where they were first extensively studied, are the solidified conduits of explosive volcanic eruptions that originated at depths of 150 to 450 kilometers in the lithospheric mantle, where pressures are sufficient to stabilize the diamond crystal structure. These eruptions were characterized by the rapid ascent of volatile-rich, mantle-derived magmas at velocities high enough to bring mantle xenoliths, fragments of deep rock, to the surface before they could re-equilibrate to lower pressure conditions. The diamonds they carried, entrained in the rising magma, were brought from depths where they had formed billions of years ago, crystallizing from carbon in the ancient lithospheric root of the cratons. Most kimberlite eruptions are ancient. None have been observed in historical time, but their solidified pipes, when exposed by erosion at the surface, represent the primary economic source of natural diamonds. Every diamond is therefore, in a deep sense, a gift from the volcanic interior of the planet. The relationship between volcanism and the global carbon cycle is both simpler and more complex than popular understanding typically recognizes, and it operates across timescales ranging from the geological to the human. At geological timescales, volcanic degassing is the primary source of carbon dioxide to the atmosphere and ocean, the geological heartbeat that, balanced against chemical weathering and biological carbon sequestration, maintains the long-term carbon cycle in a state that keeps Earth's climate within habitable bounds. At historical and contemporary timescales, the carbon dioxide emitted by volcanism annually is estimated at between 100 and 300 million tons. A figure that sounds large until compared with the approximately 37 billion tons of CO2 emitted annually by human fossil fuel combustion and land use change. Human emissions are thus approximately 100 times larger than volcanic emissions in any given year, definitively establishing the anthropogenic rather than volcanic origin of the current atmospheric CO2 increase. Yet in the aftermath of very large volcanic eruptions, the short-term climatic effects of sulfate aerosols, which produce cooling rather than warming, can temporarily mask and complicate the longer-term warming trend, creating brief windows of anomalous climate behavior within the broader context of anthropogenic change. Mount Etna, rising to approximately 3,350 meters above the eastern coast of Sicily and visible on clear days from Malta to the heel of the Italian boot, has been erupting with extraordinary frequency and in multiple different eruption styles for at least 500,000 years, making it one of the most persistently active and scientifically productive volcanic edifices on the planet. Etna's activity is driven by a complex tectonic environment where the African plate's collision with the Eurasian plate interacts with a hotspot-like mantle anomaly and the subduction of the Ionian microplate beneath Sicily, creating a magmatic system of unusual complexity and productivity. The mountain's eruptions range from gentle lava flows that slowly advance across its lower flanks to spectacular summit paroxysms that launch incandescent lava fountains hundreds of meters into the night sky and generate eruption columns visible from ships far out in the Mediterranean. Ancient Greeks identified Etna as the prison of the monster Typhon and the forge of Hephaestus. Today it is monitored by one of the world's most sophisticated multi-parameter volcanic observation networks. Its every tremor and gas fluctuation recorded and interpreted around the clock by scientists at the Istituto Nazionale di Geofisica e Vulcanologia. On the northernmost of the Aeolian Islands, a small volcanic cone barely 3 kilometers in diameter rises from the Tyrrhenian Sea to a summit of nearly 1,000 meters and has been erupting almost continuously for at least 2,000 years. A geological marathon of sustained activity that has earned Stromboli the affectionate designation of the lighthouse of the Mediterranean. Stromboli's characteristic eruption style, mild to moderate explosions from its summit craters occurring every few minutes to tens of minutes, each launching incandescent volcanic bombs and lapilli into the air before they cool in their ballistic arcs and fall back to the cone's steep Sierra del Fuoco, is so distinctive that it has given its name to a category of volcanic behavior, Strombolian activity. The mild, repetitive nature of Strombolian eruptions reflects a magma that outgasses relatively efficiently. Large gas bubbles rise through the magma column and burst at the surface in discrete explosions rather than accumulating to catastrophic pressures. This regular activity, visible from a designated observation path that thousands of hikers climb each year, makes Stromboli one of the world's most accessible and visually rewarding active volcanic experiences, a fire mountain whose perpetual performance has served as a navigational landmark and philosophical spectacle for Mediterranean seafarers across millennia. The intersection of volcanic activity and the ocean represents one of the most catastrophically consequential dynamics in natural hazard science, for when volcanoes interact with seawater, whether through flank collapse, caldera collapse, or submarine explosion, they are capable of generating tsunamis of extraordinary destructive power that carry the volcano's energy across ocean basins to distant shores with the patient inevitability of deep-water wave propagation. The 1883 Krakatoa eruption produced tsunamis reaching 30 meters in height along the Javan and Sumatran coastlines. The 2018 flank collapse of Anak Krakatau, the child of Krakatau, that had grown from the submarine remnants of the 1883 eruption, generated a tsunami that struck coastlines in the Sunda Strait with little warning, killing more than 400 people. The Hunga Tonga Hunga Hapai eruption in the Kingdom of Tonga in January 2022 produced not only a conventional water displacement tsunami but also a highly unusual meteotsunami, atmospheric pressure waves from the eruption generating secondary sea surface disturbances that propagated across the Pacific Basin, demonstrating that the ocean-atmosphere volcano interaction system contains hazard pathways not yet fully captured in existing warning systems. The January 15, 2022, eruption of the Hunga Tonga Hunga Hapai submarine volcano in the Kingdom of Tonga was, by the measure of atmospheric energy release, the largest recorded volcanic eruption since the 1991 Pinatubo event and possibly the most energetically impactful eruption since the 1883 Krakatoa explosion. The eruption column reached an estimated altitude of 58 kilometers, the highest recorded volcanic eruption column in the modern satellite era, and the atmospheric pressure wave generated by the explosive event was detected on barographs around the world multiple times as it circumnavigated the globe. The eruption occurred at a submarine volcano whose summit had breached sea level only in recent years, and the catastrophic interaction between superheated magma and ocean water drove the extraordinary explosivity of the event through a process called phreatomagmatic fragmentation. Despite its enormous atmospheric impact, the eruption's direct human toll in Tonga was relatively limited, 4 confirmed deaths, though the tsunami, ashfall, and destruction of infrastructure imposed severe humanitarian consequences on the island nation. The eruption also injected an unusual quantity of water vapor directly into the stratosphere, with potential, and still actively debated, implications for short-term climate. The birth of a volcanic island is among the most elemental spectacles in geology. The emergence of new land from the ocean's surface, built atom by atom and flow by flow from the planet's interior, a creation event observable in real time when the geological calendar happens to coincide with human timescales. The island of Surtsey, south of Iceland, was born on November 14, 1963, when a submarine eruption on the mid-Atlantic ridge broke the ocean surface in a column of steam and volcanic debris. Over the following 4 years, eruptions built the island to a maximum size of approximately 2.8 square kilometers and a height of 174 meters, before the cessation of volcanic activity allowed erosion to begin its patient work of diminishment. Surtsey has since become one of the world's most valuable natural laboratories for the study of primary ecological succession, the colonization of bare volcanic rock by life arriving from wind, ocean currents, and migrating seabirds. Within decades of the eruption's end, bacteria, mosses, and grasses had established themselves. Seabirds began nesting. Earthworms appeared in developing soils. The island is the youngest and most closely monitored example of life reclaiming territory from volcanic rock, a process that has been occurring on oceanic volcanic islands for hundreds of millions of years. The global infrastructure devoted to volcanic monitoring represents one of the most ambitious and consequential applications of geophysical science to practical human welfare, a distributed network of thousands of instruments on hundreds of volcanoes across the world's most volcanically active regions, supported by satellite monitoring systems, international data sharing agreements, and teams of scientists who stand watch over the planet's geological vital signs continuously. The Global Volcanism Program at the Smithsonian Institution maintains the definitive catalog of the world's active and recently active volcanoes, currently numbering approximately 1,500 above sea level, with many more on the ocean floor, and documents ongoing volcanic activity through weekly reports compiled from observatory networks worldwide. The Volcano Observatory's best practices program coordinates instrumentation standards and data-sharing protocols between national volcano monitoring agencies. Yet despite these impressive advances, significant monitoring gaps remain. Of the 1,500 known active volcanoes, fewer than half are monitored with any ground-based instrumentation, and the vast majority receive only the most basic satellite monitoring. The hundreds of volcanoes on the ocean floor are almost entirely unmonitored. The development of robust, low-cost monitoring systems deployable at poorly monitored but potentially hazardous volcanic centers remains one of the most important challenges in applied volcanology. The interaction between volcanic ash clouds and commercial aviation represents a hazard domain that came to global public attention only with the extraordinary disruption of European air traffic during the 2010 age of geological eruption, but which has been recognized by aviation safety engineers since the early 1980s when several aircraft flew inadvertently through volcanic ash clouds and suffered serious engine damage. Volcanic ash, comprising microscopic glass shards, mineral particles, and fine rock fragments with a hardness typically between 5 and 7 on the Mohs scale, poses multiple simultaneous threats to jet aircraft. It abrades windscreens and compressor blades. It can block fuel and air systems, and critically, at high temperatures in the engine combustion chamber, it melts and resolidifies on turbine components, potentially causing engine failure. The Volcanic Ash Advisory Centers established by the International Civil Aviation Organization provide volcanic ash trajectory modeling and issuance of volcanic ash advisories that allow aviation authorities to establish closure or rerouting corridors around ash clouds. The 2010 age of geological disruption, which grounded approximately 100,000 flights and affected 10 million passengers over 6 days, catalyzed a comprehensive review of ash concentration thresholds and aviation risk management protocols that has significantly improved the balance between safety and operational continuity. The relationship between volcanic activity and human evolutionary history extends considerably beyond the dramatic Toba bottleneck hypothesis into a subtler but pervasive influence of volcanic landscapes, resources, and environmental pressures on the evolutionary trajectory of the genus Homo. The East African Rift System, the geological structure responsible for the dramatic volcanic landscapes of Ethiopia, Kenya, Tanzania, and Uganda, provided the environmental context for much of human evolution, and researchers have argued that the intermittent volcanic activity of the rift, which periodically disrupted habitats, created new lake environments, and alternated between periods of environmental abundance and stress, may have driven the cognitive and behavioral innovations that characterize Homo sapiens. The alkaline lake systems of the East African Rift, fed by volcanic springs and surrounded by tough deposits from repeated eruptions, preserved an extraordinary fossil record of hominin evolution, including the famous footprints of Litoli, preserved in volcanic ash approximately 3.7 million years old, which document bipedal locomotion by Australopithecus afarensis in a moment of geological intimacy between volcanism and the human story. Across the deep time of Earth's geological history, periods of dramatically elevated volcanic activity, particularly the eruption of large igneous provinces, the continental flood basalt sequences created by the arrival of large mantle plumes beneath the lithosphere, have left chemical fingerprints in the geological record that correlate with major episodes of environmental disruption, biotic crisis, and mass extinction. The Siberian Traps, a large igneous province erupted approximately 252 million years ago across what is now Siberia, released extraordinary quantities of carbon dioxide, sulfur dioxide, and halogen gases over a period estimated at approximately 1 million years, contributing to the Great Dying, the end Permian mass extinction, that eliminated approximately 90 to 96% of all marine species and 70% of terrestrial vertebrate species. The Central Atlantic Magmatic Province, erupted at the end of the Triassic period approximately 201 million years ago, similarly correlates with a major mass extinction. The Deccan Traps of India, erupting in the final hundreds of thousands of years of the Cretaceous period and continuing after the Chicxulub asteroid impact, may have contributed to the end Cretaceous mass extinction alongside the asteroid's effects, though the relative contributions of the two events remain actively debated among paleontologists and geochemists. Not all continental volcanism occurs at plate boundaries or over recognized hotspots, and the existence of intraplate volcanism, volcanic activity occurring within the stable interior of tectonic plates, far from the conventional geological settings of subduction zones, spreading centers, and hotspots, represents one of the more intriguing unresolved questions in modern geodynamics. Several continental regions exhibit recently active or even currently active volcanism that does not fit neatly into the established plate tectonic framework. The newer volcanics province of southeastern Australia, which includes eruptions as recent as 5,000 years ago, the volcanic fields of Central Europe, including the Eifel region of Germany with its most recent eruptions approximately 11,000 years ago, and the complexly structured volcanic fields of the Western United States that defy simple tectonic categorization. Various explanations have been proposed for intraplate volcanism, including edge-driven convection at the boundaries of lithospheric thickness variations, small-scale mantle upwellings generated by local thermal or compositional anomalies, and the reactivation of ancient lithospheric fracture systems under the stress fields imposed by distant plate interactions. Each of these mechanisms may be partially correct, reflecting the complex three-dimensional reality of mantle dynamics beneath continents. The stratospheric consequences of major volcanic eruptions extend beyond the climatic effects of sulfate aerosols to include potentially significant perturbations to the ozone layer, the thin shield of triatomic oxygen in the lower stratosphere that protects Earth's surface from damaging ultraviolet solar radiation. Volcanic eruptions inject hydrogen chloride, hydrogen bromide, and sulfur dioxide into the stratosphere, and the sulfate aerosol particles that form from the sulfur dioxide provide surfaces on which heterogeneous chemical reactions can destroy ozone catalytically. Following the 1991 Pinatubo eruption, measurements of stratospheric ozone over middle latitudes revealed statistically significant ozone depletion in the aerosol-loaded lower stratosphere, with some studies suggesting column ozone reductions of 5 to 8% in certain regions. This depletion was relatively short-lived. As the aerosol veil dissipated over 18 months to 2 years, ozone levels recovered, but it demonstrated the potential for volcanic eruptions to temporarily exacerbate the ozone depletion caused by anthropogenic chlorofluorocarbon emissions, particularly at times when background chlorine loading of the stratosphere is elevated by human industrial activity. In the pre-industrial era, when stratospheric chlorine concentrations were at natural background levels, volcanic ozone depletion was likely considerably smaller. The relationship between volcanism and extraterrestrial material is not entirely one-directional. While volcanic processes have shaped the environments from which we search for meteorites, some meteorites themselves carry volcanic histories from other worlds that geochemists can read with extraordinary precision. The SNC meteorites, named for the three falls of Shergodi, Nakhla, and Chassigny, are recognized as Martian volcanic rocks ejected from the Martian surface by large impact events and eventually captured by Earth's gravity. Their crystallization ages, determined by radiometric dating, indicate that volcanic activity occurred on Mars as recently as approximately 170 million years ago, suggesting that Mars was not geologically dead but merely slower paced than Earth in its volcanic history. The lunar mare basalts, the dark volcanic plains that compose the face of the man in the moon visible from Earth, were erupted approximately 3 to 4 billion years ago and have been analyzed directly from samples returned by the Apollo missions. Achondritic meteorites from Vesta, the large asteroid, record a period of melting and volcanic differentiation in the early solar system approximately 4.5 billion years ago, demonstrating that volcanism was a fundamental process in the formation and evolution of rocky bodies of all sizes throughout the solar system. Mars hosts the most colossal volcanic structure in the entire solar system, Olympus Mons, a shield volcano of such stupefying dimensions that if it were placed in the American West, it would cover an area approximately the size of the state of Arizona, and its summit, at approximately 22 kilometers above the Martian datum, would extend well above the altitude at which commercial aircraft cruise on Earth. Olympus Mons stands as the geological monument to what happens when a hotspot erupts into a lithospheric plate that does not move, without plate tectonic drift to carry the crust away from the heat source and build a chain of progressively older volcanoes. The lava simply piles up in one place over billions of years, accumulating to dimensions that have no terrestrial analog. The lack of significant plate tectonics on Mars, whether because the planet cooled too quickly to maintain a sufficiently weak asthenosphere, or because its crust became too thick, or for other reasons still debated, is both the reason for Olympus Mons's extraordinary size and the reason Mars has not maintained the sustained volcanic resurfacing that keeps Earth geologically young. The youngest lava flows on Olympus Mons may be as recent as a few million years old, suggesting that the volcano may not be permanently extinct. Venus, Earth's nearest planetary neighbor and its closest twin in size, mass, and composition, presents a volcanic landscape that is both familiar and profoundly alien, a world whose surface, hidden beneath a thick, toxic atmosphere of carbon dioxide, has been mapped primarily by radar from orbiting spacecraft and found to be dominated by volcanic features of every description. From vast lava plains covering most of the planet's surface to towering shield volcanoes, unusual pancake domes, and the distinctive coronae and arachnoids that may represent a form of volcanic feature without terrestrial counterpart. Whether Venus is currently volcanically active, or whether its volcanism ceased millions of years ago in a catastrophic resurfacing event that replaced the entire surface within a geologically brief interval, has been one of the central unresolved questions in planetary science for decades. Recent analysis of Magellan spacecraft radar images has revealed what appear to be fresh, unweathered volcanic flows that were not present in earlier radar observations, suggesting ongoing activity. The European Space Agency's Venus Express mission detected thermal anomalies consistent with active eruptions, and the Da Vinci and Veritas missions planned for the coming decades are designed specifically to address questions about the current state of Venusian volcanism. Among the most deceptively dangerous and underappreciated categories of volcanic feature are Mar volcanoes, low-relief craters surrounded by shallow rims of volcanic debris, formed by explosive phreatomagmatic eruptions in which rising magma interacts violently with groundwater or surface water. The explosion when magma contacts water is driven not by volcanic gas exsolution alone but by the instantaneous flashing of water to steam, a process that can achieve explosive efficiency far exceeding ordinary magmatic eruptions. Mar craters are typically circular to elliptical, ranging from a few hundred meters to several kilometers in diameter, and their flat floors typically lie below the surrounding terrain surface because the explosion excavates existing bedrock rather than building a new volcanic edifice above the surface. The Eifel volcanic field in Germany contains numerous Mars, many of which have accumulated sediment records of remarkable completeness over tens of thousands of years, including annual laminations of pollen, algae, and mineral dust that provide some of the most detailed records of Holocene environmental and climate change in Central Europe. The volcanic lake at Mar Pulvermar, for instance, contains an uninterrupted sediment record of the past 25,000 years, offering an extraordinary archive of climate and ecological history preserved by volcanic geology. The eruption style named for the island of Surtsey, Surtsean eruptions, encompasses the distinctive character of volcanic explosions occurring in shallow water, where the interaction between erupting magma and ocean water produces the characteristic steam-dominated explosions that build new islands or enlarge existing coastlines through the gradual accumulation of volcanic material above sea level. Surtsean eruptions are characterized by their cock's tail, or cypressoid, jets, plumes of dark, wet ash and steam ejected in rapid, roiling bursts that scatter widely and fall back around the vent to build tough rings of palagonitized ash. The explosions occur when water contacts magma at rates that allow steam explosions rather than simply quenching the lava. Too little water and the lava erupts relatively quietly, while too much water cools the system without explosion. The resulting volcanic deposits, palagonite tuffs and hyaloclastites, are geologically distinctive and erosionally weak, which is why the islands built by Surtsean eruptions often rapidly diminish in size after eruptive activity ceases. Surtsey itself has lost approximately half its original area to erosion in the decades since its eruption ended, and the sea is expected to continue reducing it until only the more resistant lava core remains above water. The modern city of Naples and its surrounding metropolitan region, home to approximately 3 million people, represents one of the most serious volcanic risk scenarios on Earth, crowded into the shadow of Mount Vesuvius and the Campi Flegrei caldera system in a density of human habitation that would have been unimaginable to the Romans of the 1st century CE. Vesuvius has erupted multiple times since 79 CE, most recently in 1944 during the Allied campaign in Italy, and volcanologists broadly agree that the volcano will erupt again, though the timing cannot be predicted with useful precision. The Italian Civil Protection Department maintains an emergency evacuation plan for a zone around Vesuvius encompassing approximately 800,000 residents, and regular evacuation exercises are conducted, but the logistical complexity of evacuating nearly 1 million people in the days available after the onset of precursory volcanic signals, and the social and cultural attachments of communities that have lived on volcanic soil for generations, pose challenges that are as much sociological as geological. The simultaneous risk posed by the Campi Flegrei supervolcanic caldera system to the west of Naples, which has been experiencing ground uplift and seismic unrest since the 1980s, adds a second dimension of volcanic hazard to one of Europe's most vibrant and historically significant urban landscapes. The Campi Flegrei, the burning fields, is a volcanic system of extraordinary scientific interest and considerable public concern that underlies the western suburbs of Naples, the town of Pozzuoli, and a significant portion of the Gulf of Pozzuoli in a caldera system approximately 13 kilometers in diameter. The most dramatic aspect of Campi Flegrei's contemporary behavior is the phenomenon of bradyseism, the slow, episodic rise and fall of the ground surface over the caldera, which has been documented since Roman times and has accelerated dramatically since the 1980s. The town of Pozzuoli has experienced multiple episodes of ground uplift totaling nearly 3 meters since 1950, necessitating the evacuation of parts of the historic city center on 2 occasions when seismicity associated with rapid uplift reached damaging levels. This ground deformation is driven by the movement and pressure changes in a hydrothermal and magmatic system beneath the caldera, a system that last produced a major volcanic eruption in 1538, when the Monte Nuovo cinder cone grew from nothing to 133 meters in height over the course of a week. Understanding whether Campi Flegrei is building toward a future large eruption or will continue its restless but non-eruptive behavior constitutes one of the most pressing problems in European volcanic hazard assessment. On the island of Java, in a landscape of extraordinary agricultural density and cultural richness, Mount Merapi rises to approximately 2,930 meters above sea level and has been erupting frequently throughout recorded Javanese history, earning its status as one of the world's most active and dangerous volcanoes by any measure of eruptive frequency, hazard, and proximity of population. The name Merapi derives from the Old Javanese for fire mountain, and the mountain is regarded by some Javanese communities as the spiritual guardian of the Sultanate of Yogyakarta, whose palace is positioned on the volcano's exact meridian as a cosmological alignment of royal and volcanic power. Merapi's eruption style is characterized by the growth of viscous lava domes in its summit crater and the periodic collapse of these domes in pyroclastic flows that advance down its steep valleys with lethal speed. The 2010 eruption, one of Merapi's largest in the 20th and 21st centuries, killed 353 people and displaced 350,000 from their homes. The region on Merapi's flanks most severely impacted by the 2010 eruption is now resettled, and the dense population of the surrounding region continues to return after eruptions, sustained by fertile volcanic soils and centuries of cultural intimacy with their fire mountain. The continent of Antarctica, often conceived as a geologically frozen world of ice and geological simplicity, harbors volcanic surprises beneath its 2-kilometer-deep ice sheet and along its margins that reveal the persistence of geological dynamism even in Earth's coldest places. Mount Erebus, rising to 3,794 meters on Ross Island and visible from the McMurdo Research Station, is the southernmost active volcano on Earth and one of the few volcanoes on the planet to maintain a permanent convecting lava lake in its summit crater, a churning pool of a northoclase phonolite lava that has persisted with remarkable stability for at least 4 decades of observation. The extreme cold and clarity of the Antarctic atmosphere make Erebus one of the best-studied volcanic gas sources in the world, The isolated environment minimizes contamination, and the persistent lava lake provides a continuous emission source ideal for monitoring studies. Beneath the West Antarctic ice sheet, recent research using airborne radar and seismic surveys has revealed a cluster of subglacial volcanoes in the Marie Birdland region, including one whose eruption approximately 2,000 years ago deposited a recognizable tephra layer in deep ice cores. The interaction between volcanic heat sources and the overlying ice sheet is now recognized as a potentially significant factor in ice sheet dynamics and stability. The atmospheric chemistry of volcanic degassing extends its influence well beyond the visible ash clouds and obvious sulfurous odors to include a suite of chemical interactions that can produce acid rain, damage agricultural systems, and affect human health at considerable distances from the erupting volcano. Sulfur dioxide emitted during volcanic eruptions is oxidized in the atmosphere to form sulfuric acid aerosols, which eventually deposit on the land surface as wet or dry acid deposition, a volcanic acid rain that can acidify surface waters, damage foliage, and leach nutrients from soils over areas extending hundreds to thousands of kilometers downwind from the source. Fluorine, emitted as hydrogen fluoride in volcanic gas plumes, deposits on vegetation and soil surfaces and can reach toxic concentrations in the grass consumed by grazing livestock, causing a condition known as fluorosis that weakens bone and dental tissue. The devastating fluorosis-related livestock deaths in Iceland following the Laki 1783 eruption represent one of the most well-documented historical examples of this hazard. The VOG, volcanic smog, generated by Kilauea's continuous sulfur dioxide emissions mixing with atmospheric moisture to form sulfuric acid mist, has been a persistent air quality concern for residents of downwind areas of Hawaii, affecting respiratory health and agricultural production across the island. The volcanic landscape and its associated imagery of fire, destruction, creation, and the sublime have permeated Western art and literature for centuries with a fecundity that reflects the deep psychological resonance of erupting mountains in the human imagination. Joseph Wright of Derby's paintings of Vesuvius erupting in the 1770s, based on the volcano's historic 1774 and 1779 eruptions, which Wright witnessed during his Italian tour, are among the most celebrated depictions of the volcanic sublime in Western art, capturing the simultaneous terror and grandeur of an eruption in compositions that stage human figures against overwhelming geological theater. The letters of Pliny the Younger describing the 79 CE Vesuvius eruption, written 25 years after the event to the historian Tacitus, are among the finest pieces of observational science writing in classical literature, combining precise geophysical observation with personal narrative and emotional truth in a way that transcends generic classification. Jules Verne's Journey to the Center of the Earth established a literary tradition of volcanic interiors as portals to discovery. Contemporary novelists from Armistead Maupin to Richard Powers have used volcanoes as settings for meditations on impermanence, geological time, and the diminutive scale of human concerns against planetary processes. The scientific aspiration of volcanic eruption forecasting, the quantitative prediction of the timing, magnitude, and character of future volcanic eruptions with sufficient reliability to inform evacuation decisions and hazard management, remains one of the most challenging problems in earth science. Combining the intrinsic uncertainties of complex nonlinear systems with the immense practical stakes of decisions affecting human lives. The current state-of-the-art in eruption forecasting is built on pattern recognition and probabilistic inference from monitoring data rather than deterministic first principles prediction. As a volcanic system escalates toward eruption, the rate of seismicity, the rate of ground deformation, and the flux of volcanic gases typically increase in patterns that experienced volcanologists recognize as precursory, allowing probabilistic statements about eruption likelihood within defined time windows. The Bayesian event tree eruption forecasting tool, developed and refined by probabilistic volcanology teams in Europe and the United States, provides a formal mathematical framework for integrating diverse monitoring data streams into eruption probability estimates. Yet volcanoes can and do erupt without clearly identifiable precursory sequences, and perhaps more insidiously, they can display vigorous precursory activity that subsides without producing an eruption, creating the cry wolf, problem of public warning systems where repeated false alarms erode community trust and evacuation compliance. The three caldera-forming supereruptions of the Yellowstone hotspot system, the Huckleberry Ridge Tuff eruption at approximately 2.1 million years ago, the Mesa Falls Tuff eruption at approximately 1.3 million years ago, and the Lava Creek Tuff eruption at approximately 640,000 years ago, produced volcanic deposits that provide one of the most accessible records of supervolcanic behavior in the geological record. The Lava Creek Tuff, the most recent and most extensively studied of these deposits, ejected approximately 1,000 cubic kilometers of rhyolitic magma in an eruption that deposited recognizable ash across most of North America east of the Rockies. The caldera that formed collapsed the landscape across what is now the central portion of Yellowstone National Park to depths of several hundred meters. In the aftermath of each caldera-forming eruption, the Yellowstone system entered a period of resurgent volcanism in which the caldera floor gradually domed upward as the magmatic system recharged, and diffusive eruptions of highly viscous rhyolite lava produced enormous lava flows that filled portions of the caldera. The most recent rhyolite lava flow in the Yellowstone system erupted approximately 70,000 years ago, a geological moment that is more recent than the emergence of Homo sapiens. The Deccan Traps, from the Dutch word trap, meaning stairs, describing the step-like topography that erosion carves into thick sequences of horizontal lava flows, represent one of the most voluminous continental flood basalt provinces in the geological record, covering approximately 500,000 square kilometers of what is now the Indian subcontinent to depths of up to 2 kilometers of stacked basaltic lava flows. The Deccan eruptions were emplaced primarily between approximately 68 and 66 million years ago, a geological interval that overlaps with the Chicxulub asteroid impact and the end Cretaceous mass extinction, a coincidence that has generated substantial scientific debate about the relative roles of volcanism and impact in driving the extinction of non-avian dinosaurs and approximately 3/4 of all species then living. Proponents of a significant Deccan contribution to the mass extinction point to evidence that the eruption rate increased dramatically in the aftermath of the Chicxulub impact, possibly triggered by the seismic energy of the impact itself, and that the combined environmental stresses of volcanic outgassing and impact winter created conditions more extreme than either event alone could have produced. The Deccan Traps remain a geological monument to the planet's capacity for prolonged, high-volume volcanic eruption and its consequences for the living world. The geological record of the Archean, Earth's earliest geological epoch, extending from approximately 4 billion to 2.5 billion years ago, preserves evidence of a style of volcanism that no longer occurs on Earth today: the eruption of komatiite lavas, ultramafic magmas so rich in magnesium and iron and so deficient in silica that they achieved eruption temperatures between 1600 and 1800 degrees Celsius, generating lavas that flowed with a fluidity approaching that of water. Komatiites are recognized in the ancient Archean terrains of Zimbabwe, Australia, South Africa, and Canada by their distinctive spinifex texture, a crystallographic pattern of large, skeletal olivine crystals that can only form by rapid cooling of extremely hot, magnesium-rich magma. The eruption of komatiites on the early Earth reflects a planet considerably hotter than today, with higher rates of internal heat production from radioactive decay, producing mantle temperatures that could generate magmas of compositions impossible under the cooler thermal conditions of the modern Earth. The last significant komatiite eruptions occurred approximately 1.9 billion years ago in what is now Canada. Their study provides a window into a geologically alien early Earth, a world of fire and heat whose volcanic character was as different from our own geological experience as Io's is from Earth's. The crater lakes and caldera lakes of volcanic systems represent some of the world's most chemically extreme and scientifically valuable aquatic environments, bodies of water whose properties reflect the ongoing volcanic and hydrothermal activity of the systems within which they sit. Lake Nyos in Cameroon occupies the crater of a Mar volcano above an active magmatic system, and its deep, cold waters have accumulated an enormous reservoir of dissolved carbon dioxide from magmatic degassing over centuries, a geological time bomb that discharged catastrophically on August 21, 1986. when a landslide or atmospheric disturbance triggered the overturn of the deep CO2-saturated waters. The resulting Ling-Nik eruption, the sudden release of dissolved gas from a CO2 supersaturated lake, expelled an estimated 1 cubic kilometer of carbon dioxide and water from the crater in a wave of suffocating gas that swept through surrounding valleys, killing approximately 1,746 people and 3,500 livestock within a radius of 25 kilometers before the heavier-than-air gas dispersed. Lake Manaun, another Maar lake in Cameroon, experienced a similar though smaller Ling-Nik eruption 2 years earlier. Degassing systems have since been installed in both lakes to prevent further CO2 accumulation, drawing deep water to the surface through pipes to allow controlled degassing. Among the most hazardous and least predictable categories of volcanic eruption are phreatic eruptions, explosions driven not by the direct pressure of volcanic gas exsolving from magma but by the violent flashing of groundwater, surface water, or hydrothermal water to steam when it contacts hot volcanic rocks. Because phreatic eruptions require only heat and water, not necessarily the movement of fresh magma toward the surface, they can occur with minimal precursory warning from the seismic and ground deformation signals that typically indicate magma ascent, making them particularly dangerous for people in volcanic areas who may have received no official warning to evacuate. The eruption of Ontake volcano in Japan on September 27, 2014, was a phreatic event that killed 58 hikers on the summit trails in a matter of minutes, making it the deadliest volcanic disaster in Japan since the 1926 Tokachi Dake eruption. With no magma reaching the surface, the eruption had produced only minor seismic precursors that were insufficient to trigger a warning under the monitoring protocols then in place. The disaster prompted major changes in Japanese volcanic monitoring and public warning systems. White Island in New Zealand, another hydrothermally active but frequently visited tourist destination, suffered a deadly phreatic eruption in December 2019, killing 22 visitors. The correspondence between volcanic geological activity and high biodiversity in several regions of the world reflects multiple causal mechanisms by which volcanism promotes rather than diminishes biological richness over geological timescales. The volcanic island systems of the Pacific, Hawaii, the Galapagos, the Society Islands, are celebrated centers of endemism precisely because their volcanic origin created biologically clean slates, isolated from continental biotas by vast oceanic distances, upon which evolution could proceed without the constraints imposed by competition with long-established continental species assemblages. The Central American volcanic arc, where subduction of the Cocos Plate beneath the Caribbean Plate maintains a chain of active stratovolcanoes from Guatemala to Costa Rica, is embedded within the biodiversity corridor of Mesoamerica, one of the world's richest biological regions, where fertile volcanic soils, diverse microclimates created by topographic relief, and the geological dynamism of the volcanic landscape have collectively promoted the evolution and maintenance of extraordinary biological diversity. The African Albertine Rift, where the Virunga volcanic chain rises from the Great Rift Valley, provides habitat for mountain gorillas and an exceptional diversity of plant and animal species in high-altitude volcanic landscapes that have served as refugia during historical climate fluctuations. The volcanic and geothermal activity that poses hazards to communities living in its proximity simultaneously offers those communities a renewable energy resource of potentially enormous value. Geothermal energy, derived from the heat stored in volcanic rocks and hydrothermal systems at accessible depths, is one of the most dependable and geographically consistent renewable energy sources available. Iceland, with its geologically unusual combination of hotspot volcanism and divergent plate boundary activity, has developed geothermal energy most extensively of any nation. Approximately 90% of Icelandic homes are heated by geothermal hot water piped from subsurface reservoirs, and nearly 30% of the nation's electricity is generated by geothermal steam power plants. The city of Reykjavik, powered by hydroelectric and geothermal energy, produces relatively low per capita carbon emissions despite its location in a cold climate that demands considerable space heating. Kenya's Olkaria geothermal field in the East African Rift Valley provides approximately 45% of Kenya's installed electricity generation capacity, serving as a model for geothermal development in volcanically active developing nations. The global potential for geothermal energy development in volcanically active regions, including Indonesia, the Philippines, Central America, and the Western United States, represents a significant and underutilized component of the global renewable energy portfolio. The documented global cooling effect of large volcanic eruptions has inspired proposals in the controversial emerging field of solar geoengineering, sometimes called solar radiation management, to deliberately mimic the volcanic aerosol effect by injecting sulfate particles or other reflective materials into the stratosphere to counteract global warming. The idea, known as stratospheric aerosol injection, would involve aircraft, balloons, or other delivery systems releasing particles that would spread through the stratosphere and reflect a small percentage of incoming solar radiation back into space, reducing surface temperatures on a globally averaged basis. Proponents point to the efficacy of natural volcanic precedents. The Pinatubo eruption cooled the globe by approximately 0.5 degrees Celsius for roughly 2 years, and argue that a controlled, sustained deployment could achieve similar effects with deliberate management of dosing, particle properties, and distribution. Critics raise concerns about unintended consequences, including disruption of monsoon precipitation, regional inequities in the distribution of climate effects, the governance challenges of an intervention that would require sustained global coordination, and the risk of termination shock, a rapid temperature rebound if the injection program were suddenly discontinued, as well as the fundamental question of whether technological management of symptoms rather than the underlying cause represents sound long-term strategy. The volcano's power over human imagination has made it a recurring and symbolically potent presence in science fiction and speculative literature, where erupting mountains serve variously as backdrops for adventure, metaphors for technological hubris, portals to alien worlds, and meditations on the relationship between civilization and geological time. J.R.R. Tolkien's Mount Doom, Orodruin, the volcanic heart of Mordor in The Lord of the Rings, draws explicitly on volcanic mythology, placing the climax of the epic in a landscape that is simultaneously geological and moral, where the fires that forge the Ring of Power are the same fires that must ultimately unmake it. Tolkien's descriptions of Orodruin's eruptions draw on imagery that has since been recognized as geologically informed by modern volcanologists. The periodic explosions, the lava fountains, the suffocating gases, and the pyroclastic flows that accompany Frodo and Sam's final ascent suggest an author who had studied volcanic descriptions with care. In cinema, the volcano serves recurring narrative functions, as a source of apocalyptic threat in disaster films, as the geological dwelling of mythological beings in animated features, and as a setting of hostile alien otherness in science fiction landscapes, always carrying its cultural freight of power, danger, and elemental sublime. The magma chamber, that reservoir of molten rock within the crust that feeds volcanic eruptions at the surface, has long been conceptualized as a simple tank of liquid magma awaiting sufficient pressure to erupt. Modern petrological and geophysical research has substantially complicated and enriched this picture, revealing that most magmatic systems spend the majority of their existence in a state of partial crystallization, a crystal-rich mush, in which liquid melt is distributed in varying proportions through a framework of crystallized minerals, with fully molten regions constituting only a small fraction of the total magmatic volume at any given time. The magma mush, model of volcanic systems has important implications for eruption dynamics. Eruptions may be triggered not merely by the addition of new magma to the system but by events that mobilize and consolidate the dispersed melt within a crystal mush, potentially on timescales far shorter than the slow geophysical processes of magma recharge would suggest. Earthquakes, pressure changes, or the intrusion of fresh hot magma from depth can all potentially destabilize a mush system, extracting and aggregating melt into a mobile, eruptible body on timescales ranging from decades to weeks to, potentially, days. Understanding these mobilization processes is central to the challenge of eruption forecasting at systems that have been dormant for centuries or millennia. One of the most elegant demonstrations of the plate tectonics theory, and of the relative motion between tectonic plates and stationary mantle plumes, is provided by the age progression of volcanic island chains, where the radiometric ages of volcanic rocks from successive islands in a chain increase systematically with distance from the current active volcanic center over the hotspot. The Hawaiian Emperor Seamount chain provides the most celebrated and well-studied example. Volcanic rocks from the Big Island of Hawaii are less than 500,000 years old, while those from Kauai are approximately 5 million years old, and those from the Emperor Seamounts, the portion of the chain that extends northward toward the Aleutian Trench, increase in age to approximately 80 million years. The sharp bend in the chain at approximately 43 to 47 million years ago, where the chain changes direction from northwest to north, has been interpreted as evidence of a change in the direction of Pacific Plate motion at that time, though some researchers argue it alternatively or additionally reflects a shift in the position of the hotspot itself. The Hawaiian chain thus serves simultaneously as a geological conveyor belt, an age-progressive record of volcanic island construction, and a sensitive monitor of the deep mantle dynamics that generate the hotspot. Iceland's position straddling the mid-Atlantic ridge makes it the only place on Earth where the mid-ocean ridge system emerges above sea level to become continuously observable, offering volcanologists, tectonophysicists, and geologists direct access to the process of seafloor spreading as it operates on land. Across Iceland, from the Reykjanes Peninsula in the southwest to the Jorns Fracture Zone in the northeast, the land is continuously pulled apart along the ridge's divergent spreading axis at rates of approximately 2 centimeters per year, a motion that has created the spectacular rift valleys, normal fault escarpments, and volcanic fissure systems that characterize Iceland's tectonic landscape. The 2021 Fagradalsfjall eruption on the Reykjanes Peninsula, which began after nearly 800 years of volcanic quiet in that area, brought lava flows to within a few kilometers of the Reykjavik capital region and attracted hundreds of thousands of visitors who could safely approach and observe lava flows from only meters away. A spectacle that made global headlines and provided extraordinary scientific documentation of a new effusive basaltic eruption from its very first hours. The eruption continued for 6 months, followed by additional eruptions in 2022 and 2023, suggesting the awakening of a new period of volcanic activity in the Reykjanes Peninsula after its extended dormancy. Ice cores drilled from the Greenland and Antarctic ice sheets and analyzed in climate research laboratories have revealed an unexpected archive of volcanic history. The sulfate aerosols deposited by major volcanic eruptions over the past hundreds of thousands of years have preserved their chemical signature in the annual ice layers, creating a detailed chronological record of explosive volcanic activity that predates any written historical documentation. By measuring the concentration of sulfate in ice core layers and comparing it with background sulfate levels from non-volcanic sources, researchers can identify the timing and approximate magnitude of past eruptions and correlate these volcanic signals with other climate proxy records in the ice, oxygen isotope records of temperature, dust content reflecting wind patterns and aridity, methane and carbon dioxide from trapped air bubbles, to understand how volcanic eruptions have interacted with climate variability across multiple timescales. The synchronization of ice core records from Greenland and Antarctica allows researchers to distinguish northern hemisphere, southern hemisphere, and globally distributed eruptions based on whether their sulfate signals appear in one or both ice sheets. This volcanic chronology has been extended back more than 800,000 years in the Antarctic Epica ice core, providing an unprecedented record of Earth's volcanic pulse across multiple glacial-interglacial cycles. The composition of volcanic gases emitted to the Earth's atmosphere has not remained constant across geological time but has evolved as the planet itself has evolved, reflecting changes in the composition of the mantle from which magmas derive, the cycling of surface materials into the mantle through subduction, and the changing redox state of the planet's interior. In the early Archean Earth, volcanic gases were likely more reduced, containing more hydrogen, hydrogen sulfide, and methane relative to the oxidized species of sulfur dioxide and water vapor that dominate modern volcanic emissions, reflecting the more reduced state of the ancient mantle before the Great Oxidation Event approximately 2.4 billion years ago transformed Earth's surface and atmosphere. The rise of atmospheric oxygen, driven by biological photosynthesis, gradually oxidized not only the atmosphere and ocean but, through the subduction of oxidized seafloor sediments back into the mantle, the mantle itself, changing the oxidation state of the volcanic gases emitted at subduction zone volcanoes over billions of years. This geological feedback loop connecting life, atmosphere, ocean, and volcanic systems represents one of the most profound examples of how the biosphere has shaped the geosphere over Earth's history, a planetary coevolution of life and geology that continues today. The capacity of satellite remote sensing to monitor volcanic activity across the entire globe, including the vast majority of active volcanoes that lack ground-based monitoring infrastructure, has transformed our understanding of the global distribution and frequency of volcanic unrest and eruption in the past 2 decades. Thermal infrared satellites detect elevated temperatures at volcanic craters, lava flows, and dome surfaces. Ultraviolet instruments measure sulfur dioxide emissions from eruption plumes with extraordinary sensitivity. Radar interferometry measures ground deformation across entire volcanic edifices, and optical imaging detects ash clouds, lava flows, and eruption columns in real time. The Global Sulfur Dioxide Monitoring Project using satellite instruments has compiled a decade-long record of volcanic SO2 emissions from hundreds of volcanoes globally, revealing that the most prolific volcanic gas emitters are often not the most frequently reported eruptions but include quietly degassing open conduit systems whose continuous low-level emissions aggregate to significant atmospheric sulfur budgets. The combination of satellite monitoring with increasingly sophisticated machine learning algorithms for processing and interpreting the vast data streams from these instruments is opening the prospect of genuinely global volcanic monitoring, a system that could detect the onset of volcanic unrest at any of the world's active volcanoes with equal sensitivity, regardless of whether that volcano has ground-based instruments or not. The future of volcanology as a scientific discipline is being shaped by a convergence of technological, computational, and conceptual advances that promise to transform both the fundamental understanding of volcanic systems and the practical capacity to anticipate and mitigate volcanic hazards. Dense seismic networks equipped with low-cost MEMS sensors and cloud-connected data transmission are making comprehensive monitoring deployable at volcanoes that previously could afford only sparse instrumentation. Machine learning algorithms trained on large datasets of precursory volcanic behavior are beginning to automate the pattern recognition that previously required years of expert training to perform reliably. High-resolution numerical simulations of magmatic systems, resolving the thermomechanical behavior of magma mush zones, conduit flow dynamics, and eruption column physics at scales previously inaccessible to computation, are providing theoretical frameworks to interpret monitoring signals with greater physical realism. The growing interdisciplinary community of volcanologists is increasingly integrated with social scientists, psychologists, urban planners, and emergency managers in recognition that the scientific challenge of understanding volcanoes is inseparable from the human challenge of managing volcanic risk in communities that have lived alongside and been shaped by their fire mountains for as long as human beings have walked the earth. To contemplate the comprehensive mystery of volcanism is ultimately to contemplate the nature of the earth itself, to recognize that the ground beneath every human settlement, every agricultural field, every city and coast and wilderness, is not the static foundation it appears to be but the thin, cooling skin of a planetary body still in the process of becoming. The magma that presses against the crust in 1,000 subduction zones and rift valleys and hotspot columns is the same primal material that assembled this planet from the dust of a stellar explosion 4.5 billion years ago. The gases that volcanic eruptions release into the atmosphere are the same gases that built the air and water that sustain all life on Earth. The heat that drives volcanic convection is the slowly fading warmth of radioactive elements forged in the hearts of long dead stars before our own sun was born. Every eruption is therefore not merely a geological event but a communication from the planet's interior, a reminder, delivered in fire and ash and sulfurous cloud, that the Earth is alive in a sense that transcends biology, that the landscape we inhabit is provisional and temporary and beautiful precisely because it is neither fixed nor permanent, but perpetually, magnificently, catastrophically making itself anew.